Let's explore the relationship between the linear independence of a set of vectors, solutions to an associated homogeneous system of equations, and the idea of redundancy, using this activity from Austin's linear algebra text. If you're watching on EdPuzzle, feel free to respond to the prompts as they arise. First of all, let's recall what it means for a set of vectors to be linearly independent in the first place. First of all, remember this is a property that applies to sets of vectors. So we'll say that the set of vectors, v1, v2, up through vn, is linearly independent if, when we take these vectors and combine them together using what operation? Using the operation of linear combination. If I take a linear combination of those vectors and the result is 0, then this implies, in other words, that this can only happen under what condition? The condition that all of the weights in my linear combination are equal to 0. In other words, linear independence of a set of vectors means that the only way that a linear combination of those vectors will come out to 0 is if that linear combination has all of its weights equal to 0 in the first place. Another way this is commonly phrased is to take the equation that this sets up for this set of vectors, which is called what kind of equation? That's called the homogeneous equation in the vectors v1 up through vn. So another way to say this is that a set of vectors is linearly independent when the homogeneous equation for that set of vectors only has this solution, and this solution gets called the trivial solution. So another way to use vocabulary in thinking about what linear independence means is that a set of vectors is linearly independent if the homogeneous equation for those vectors only has the trivial solution. So the only way to make a linear combination of those vectors 0 is to choose the weights in that linear combination to all be 0. So now let's look at this activity and how this property of linear independence wears a couple of different hats. First of all, let's think about homogeneous equations again. And the question is, if I have the equation, the homogeneous equation, ax equals 0, where a is a matrix, x is a vector, 0 is the 0 vector here. Why is it that that equation is always consistent even if we don't know anything about the matrix A? Well, the reason that this equation is always consistent is that there's a vector I can always put in for x that will make this equation true. Namely, I can always put the 0 vector in for x. That is always a solution of this equation. Why? Because the linearity properties of matrix multiplication guarantee that no matter what matrix A that I have, if I multiply A times the 0 vector, the result is always going to be the 0 vector, no matter what weird nasty matrix capital A might happen to be. So we don't need to know anything about A to conclude that this is always a consistent equation. So why is this a more interesting question than it seems? Well, it's not really so much a matter of consistency, whether or not there is a solution. It's really more about how many solutions might there be. Because to say that the 0 vector is a solution is not to rule out that there might be other solutions as well, depending on the matrix. So now we'll turn and look at this matrix A. 3, 2, 0, negative 1, 0, negative 2, 2, 1, 1. And we're going to call the columns in that matrix v1, v2, and v3. So I've highlighted them here in 3 colors. So the first question is, how do we know whether or not the 3 columns in this matrix are linearly independent or linearly dependent? And the key here is that we have a computational tool that we can apply to the matrix A. Namely, if I can study the matrix A, I can find a property of A that will tell me whether or not its columns are linearly independent. What property must A have in order for us to conclude the independence of the 3 columns? We need to know that A has a pivot in every, well, remember that pivots can exist in every row or every column, so which one do we need here? A pivot in every row or a pivot in every column? Since the issue here is about the independence of the columns, we will say that these columns are linearly independent if and only if each column has a pivot. Remember, pivots were, in the beginning of our course, kind of the markers of independence. And columns or rows which don't have pivots correspond to columns or rows that are not really adding much to our system of equations, is the way we were thinking about it before. So we can know then if the columns are independent by figuring out whether every column of A has a pivot. So to find out, we just have to row reduce the matrix. So when you do the row reduction on this matrix A, go ahead and do that now. How many pivots do you see? The echelon form of this matrix happens to look like this. Using Sage, to skip a couple of hand calculations if you like, I'm just going to enter in the matrix A and then ask for the echelon form. And we'll see what happens. There's my matrix in its echelon form. So after we've done enough row operations to get as many ones on the diagonal as we can and zeros underneath, how many pivots do you see here? That's right. There are 2 pivots in this particular matrix. And therefore, this matrix has 2 pivot columns. So what then do we conclude about the 3 columns of this matrix? Are those columns linearly independent, or are they not linearly independent, given that we've just discovered that 2 out of the 3 columns have pivots? That's right. In order to be linearly independent, all the columns had to have pivots. That didn't happen, and so we have to conclude that this set of 3 vectors is not linearly independent. So we now know that these 3 columns, these 3 vectors, are not each telling their own unique story, in a sense, that there's at least one of them that is redundant with the others. And so we're going to explore a little bit more about what that means. Here's the row echelon form of this matrix again, and we're going to go back into Part C. Part C asks us to give a description of the solution space of the homogeneous equation AX equals 0 for this matrix A. Now remember, we knew, based on Part A, even before we were introduced to a particular matrix, we knew that the homogeneous equation was always consistent. It always had a solution. But the question now is, what does the space of all solutions to the homogeneous equation for this matrix look like? So to figure that out, we just need to throw in the 0 vector somewhere. Where can I put my 0 vector into the work that I've already done in order to conclude this question pretty quickly? Right, all I need to do is put the 0 vector on the right-hand side of an augment bar in my row echelon form. Really, I should have done that back here before I started row reduction, but remember, the great thing about zeros is that elementary row operations are not capable of destroying zeros if I have all zeros on my right-hand side. So if I started with all zeros on the right-hand side of this augmented matrix, I would still have all zeros on the right side of my row echelon form. So I can just put my 0 vector there, and then use this information to describe in parametric form the solution space. And remember, when we're describing in parametric form, the first question is, what are my free variables? So what are my free variables that this row echelon form is telling me? That's right, free variables correspond to the columns without pivots. And therefore, the only column without a pivot in my row echelon form is the column that corresponds to my 3rd variable, which I'm going to call z. And so z is my free variable. Now what do you do with a free variable when you're forming a parametric description of a solution space? This is where the parametric gets its name. You set that free variable equal to a parameter, which usually we'll call t for starters, but if we have multiple, we might start using s and r and u and letters like that. But t is usually the most friendly parameter name that we use for this. So now that I know that z is going to be a free parameter t, all I have to do is use the other equations, the other rows, to solve for the basic variables x and y in terms of the free variable. So in the first row, x plus 2z is equal to 0, but z is another name for my free parameter t. So I'll put a t in place of my z, and I find out that x is negative 2t. Same thing for this second row, y minus 3z is equal to 0, but again z is my free parameter t. So y is equal to 3t, and I now have a parametric description of my solution space. What would I need to do if I wanted to turn this parametric description into a parametric vector description? Right, all that I need to do is take my 3 equations and 3 quantities and bundle them together so that my x, y, and z all belong to a 3-component vector, and same thing with on the right-hand sides. So I'll bundle my x, y, and z together into a vector. I'll bundle my coefficients of t, negative 2, 3, and 1, into a vector, factor my t out, and this often gets called the parametric vector description of the solution space. Remember, what this is saying is that for any value of t, any real number that I choose, this vector is going to be a solution of the corresponding system of equations. So if we're going to think about that solution space inside of 3 dimensions, what is that solution space going to look like? Right, if I plot the vector negative 2, 3, 1 inside of 3 space, And then I think about what's going to happen when I multiply that negative 2, 3, 1 by an arbitrary real number t. Well, that's just going to scale my vector, either in a parallel fashion if t is positive, or in an anti-parallel fashion for all the negative t, and as t ranges over all the real numbers, I'm going to get a whole line's worth of solutions. So my solution space for this homogeneous equation is this entire line that goes in the direction of negative 2, 3, 1 and passes through the origin. Another way to say this is that the solution space is the span of the vector negative 2, 3, 1 inside of 3 space. So that concludes our description of the solution space. What we need to do now is tie this back to the original definition of linear independence. And that's what happens in part D. So in part D, the observation is we know that 0 is a solution to the homogeneous equation. We also went through the trouble in part C of coming up with a description of the solution space of the homogeneous equation. So how, then, do we answer the question of find me some weights, C1, C2, and C3, such that C1V1 plus C2V2 plus C3V3, this should say C3, C3V3, is equal to 0. Well, as a matrix product, how do I understand the left-hand side of this equation? If I have a linear combination of the vectors v1, v2, and v3, what's another way to write that linear combination using a matrix? Right, this is exactly what we meant when we talked about what it means to multiply matrix times vector. The vector here is the vector whose entries are just the weights, c1, c2, and c3, and the matrix by which it is being multiplied on the left is a matrix whose columns are v1, v2, v3. Remember, this is what matrix times vector means. Matrix times vector means take a linear combination of the columns of that matrix, whose weights are given by the entries of the vector that we're multiplying by. So in other words, just by interpreting this linear combination as matrix times vector, what we find out is that we come up against a question that we've already solved. Where did we already solve this? That's right, we just solved it a second ago in part C. We described the solution space of this particular system of equations completely. The only difference is that we used the letters x, y, and z to describe those weights when we did it in part C, and now we're just using C1, C2, and C3. They're just different names for the same thing. This is a problem that we've already solved. So if I want to use this solution to find weights such that this linear combination is equal to 0, what do I need to do? I have the parametric description of the solution space. If I want to find a set of weights, C1 and C2 and C3, that solve this equation, but where those weights are maybe non-trivial, let's say we want at least one of them not to be 0, because we know that always is a solution, but if we want an interesting solution, how do I find one? Since this is a description of all possible solutions for any value of t, any real number that's selected, to find any old solution, we can just put on our specificity hat and we can choose a value for t. Let's just pick a random t out of a hat. As long as I don't pick 0 for my t, I'm going to get a C1, C2, C3 that is a non-trivial solution to this system. So for example, let's suppose that I just pick a simple number like 1 for my t. If I plug in a 1 for my t, then I'm going to get C1, C2, and C3 is this vector times 1, or negative 2, 3, 1. We can check that if I take negative 2 times this vector, that's going to give me negative 6, 2, negative 4. I add it to 3 times this vector, which is going to be 6, 0, 3, and I add to that 1 of this vector. Then when I add that linear combination of these 3 vectors together, I do indeed get the 0 vector for that linear combination. So there then is a non-trivial solution of this homogeneous equation. So, and now this is the big connection of this video coming here at the end. What does this tell me about linear independence? Why have we just proven that this set of 3 vectors is not linearly independent? Looking at the original definition, remember that the original definition says that linear independence means that the homogeneous equation being satisfied implies that all of the weights must be 0. So why have we falsified that statement? Remember, anytime you falsify an implication, an if-then statement, the only way to falsify an if-then statement is to find a case in which the premise is true, but the conclusion is false. In other words, we need to show that it's possible for the first thing to happen, but the second thing to fail. That's the only way to make this implication false for my set of 3 vectors. And we just found out that that does in fact happen, because this C1, C2, and C3 give me a linear combination of these 3 vectors, which is equal to 0, so the premise is satisfied, and yet that C1, C2, and C3 are not in fact all 0. So the conclusion is not satisfied. So that's why the work that we just did proves that this set of 3 vectors is not linearly independent. It's not linearly independent because it's possible to make a linear combination of those vectors equal to 0, but that all of the weights are not equal to 0. In fact, even if only one of these were not equal to 0, we would be still falsifying this conclusion, right? That to say that it only has the trivial solution means the only way to get 0 is to make all the weights 0. But clearly, this is not such a case. So the work we've done shows that these vectors are not linearly independent. Also, we chose t equals 1 before. We could choose t equals any real number and get a different linear combination that can also make this set of vectors equal to 0. So if I choose t equals -5, for example, then my C1, C2, and C3 are going to change. I put them into my equation, and I get an equation that looks a little different, and yet this equation will still be satisfied for this set of weights and this set of vectors v1, v2, v3. 10 of these plus -15 of those plus -5 of those is still going to give me the 0 vector. So there's infinitely many different solutions to this homogeneous equation, but they're all parameterized by multiples of the vector -2, 3, 1. That's this line inside of R3. So to finish, we want to tie this back to the idea of redundancy. We know now, both based on the work we did and based on falsifying the definition, that this set of 3 vectors is not linearly independent. So our hunch is that that means that there's redundancy, that one of them is telling the same story as the other 2. So in part E, we just want to use the work that we've done to figure out how to make that specific. How do I write one of my vectors in terms of a linear combination of the others? All I really want to do then is solve, let's say, this equation, which relates v1, v2, and v3 together. I can solve that equation for a quantity that will make my case. What should I solve it for? I'll solve it for one of the vectors. Let's say we solve it for v3, for example. If I rearrange this equation to get the v3 by itself, subtracting the v1 and v2 terms from both sides and then dividing by -5, I find out that v3 is twice v1 minus 3 times v2. In other words, this third column is not independent of the first 2, because this third column is twice the first column minus thrice the second column. So 2 of these minus 3 of those gives me the third column. And that's another way of expressing why this set of 3 vectors is not linearly independent. Because the third one actually lies in the span of the other 2. It is equal to a linear combination of the other 2. So taking a broad look back at what we just did, linear independence, first and foremost in its original definition, is about solutions of the homogeneous equation for that set of vectors. Linear independence means the only way to satisfy the homogeneous equation for that set of vectors, the only linear combination that gives me the 0 vector, is the linear combination whose weights are all 0, called the trivial linear combination. But computationally, how we unravel that is by using the tools of solving a homogeneous equation and figuring out whether a non-trivial solution exists. And a non-trivial solution can only exist if we have a free variable in my system. And I'm going to have a free variable, in this case it was z, which turned into my free parameter t. I'm going to have a free variable exactly when at least one of my columns doesn't have a pivot. And so it was the fact that this third column didn't have a pivot in the echelon form that gave me a free variable, that gave me a non-trivial solution to this system of equations, and that's exactly why the definition of linear independence gets falsified. Because whenever there's a non-trivial solution, this equation is satisfied, so the premise is satisfied, but the conclusion that the weights are all trivial is not satisfied. So anytime we have a free variable, that gives me non-trivial solutions to the homogeneous equation, and that gives me non-linear independence.